Hi guys, I am Neeraj Toshniwal. I am currently studying at IIT Bombay doing my BTech in computer science, and I have all secured an AIR of 21 in ITJ 2009 and was also a gold medalist at National Chemistry Olympiad 2009. So I am here now to teach you the advanced level of chemical bonding. We are done with the basic or foundation level of chemical bonding. Now I will give you some illustrations on the concepts of chemical bonding, because the periodic properties and chemical bondings are the chapter that in these the theory is very more, but unless you practice more and more questions you will not have the good grasp of the concepts. So let me start with some illustrations that have been asked in JEE also, and some brainstorming questions. So let's start. First question number 1. So in this illustration I will tell you how to apply the Born-Haber cycle to calculate the lattice enthalpy of any given solid. So we have to calculate the lattice enthalpy of solid Kf, for which we are given all the other quantities, that is delta H sublimation and dissociation. All the other enthalpy change are given to us, and we have to calculate the lattice energy. So what are we given? I will just write it. So we are given the net enthalpy change for Kf is given as minus of 562.5 kilojoule per mole, 562.5, yeah. And then delta H sublimation of potassium is given as 89.6 kilojoule per mole. That is, we have to supply an energy of 89.6 kilojoule per mole to change its states from solid to liquid, from solid to gas. IE1 of potassium is given as 419 kilojoule per mole. That is first ionization energy. To knock out the first electron from potassium, we have to give an energy of 419 kilojoule per mole. Dissociation of F2, delta H dissociation of fluorine molecule is given as 158.2 kilojoule per mole. That is, you have to give an energy of 158.2 kilojoule per mole to dissociate a molecule of F2 into 2 fluorine atom. Then the electron affinity of fluorine atom, first electron affinity of fluorine atom is given as minus of 332.6 kilojoule per mole. So you have to calculate the lattice enthalpy. So what would be the reaction? Reaction would be the potassium in solid state plus half of fluorine in the gaseous state gives Kf in the solid state. Fine. So what would be the reaction? Reaction would be the delta HF, that is the overall net enthalpy change. I am using here the Hess law of constant heat summation, that is net enthalpy change of a reaction is always equal whether it takes in one step or it takes place in several steps. So delta HF, that is the net enthalpy change, would be equal to, first I have to apply the delta H sublimation, that is bring it into the gaseous state. So it would be delta H sublimation here. Then we have to apply the first ionization energy of potassium, that is which will in turn change into potassium ion, first monovalent cation of potassium minus electron. So it would be first ionization energy of potassium. Then it would be the delta H dissociation, and since we are using only half of mole, so we will use half into delta H dissociation for fluorine molecule, so it will give us the fluorine atom. Then we will have to use first electron affinity of fluorine, that is plus, so it will give us F minus G, and these will combine to give us the lattice enthalpy. So it would be delta sublimation plus first ionization energy plus half into delta H dissociation plus electron affinity 1 plus lattice energy or lattice enthalpy. So putting the values, clubbing the values, it would be minus 562.6 equals to 89.6 plus 419 plus half into 158.2, because we are using only half mole of fluorine molecule, so it would be 79.1 plus first electron affinity, so it is negative, so I just put a negative sign here, minus 332.6 plus the lattice enthalpy. So when you add this up, you will get, or I should do the calculation also. So it is 89.6 plus 419, so you will get 506 or 508 in turn, 508.6 plus 79.1 minus, or so this would be the minus 0.5 and this would be 3 and this would be equals to 5, so it would be 253.5. Fine. So just check the calculation. Is this correct or not? I think it's correct. So plus lattice enthalpy. So when we subtract it from here, we will got 0.1 and it would be 5, again 5 and 2 plus lattice enthalpy. So it will be positive. So lattice enthalpy would be equals to minus of 562.6 minus 255.1. So lattice enthalpy is minus of 0.7, this is 718. So it is coming out to minus 817.7 kilojoule per mole, but actually it is not the lattice enthalpy, it is the negative of the lattice enthalpy, I should rather say. So I would say lattice enthalpy negative, lattice enthalpy negative, lattice enthalpy negative, because the lattice enthalpy is defined as the energy required to break the solid into its ionic into its gaseous constituents. So it is the opposite of that, therefore it should be lattice enthalpy negative. So the lattice enthalpy is in turn equals to 817.7 kilojoule per mole. So this is the illustration which explains how to apply Born-Haber cycle and use the Hess law of constant heat summation. Yeah. So I will try to cover the questions on all the concepts which I have taught you in the foundation level of chemical bonding, so that you can get a good feel or good grasp of the topics, because it is very important to solve as many questions as possible as far as chemical bonding is concerned, as it is of great importance in the JEE also. So second is a subjective question also, that is asked is explain the hydrolysis in BCl3 and BF3. So first I will explain you what is the hydrolysis, just remind you what is the hydrolysis. Hydrolysis is the reaction of water molecules with the molecule in which ultimately it leads to the breakdown of water molecule into H plus and OH minus ion. So let us see what is hydrolysis done when of BCl3. So BCl3 has 3 bond pair, no lone pair, sp2 hybridization, trigonal planar in shape. So when a water molecule attacks it, because oxygen has 2 lone pair, sp3 hybridization, 2 bond 2 lone pair, so it is a bent V-shaped, so to say V-shaped structure, angle of 104 degree, as I told you in the advanced level. So I will just keep on repeating all these terms, because it would be quite easy. In this way it would be quite easy for you to remember these values, as these are frequently asked in the J. So this attacks here, this oxygen attacks here, because of this bond gets weakened and this HCl in turn gets separated. So what happens is that it forms BOH Cl Cl plus HCl. Now there are 2 more chlorine present and water we are hydrolyzing, so there is no limiting reagent of water, so the other 2 Cl will also be replaced. So the net reaction would be the addition of 3H2O, which will result in BOH whole thrice plus 3 molecules of HCl. This is the hydrolysis of boron, because the boron has a vacant p orbital and the oxygen has the lone pair, so this attack will take place. So in case of BF3 also, what happens if BF3 attacks? So in BF3 also B has the vacant p orbital, so 3H2O will attack, it will form the same BOH whole thrice plus 3HF. But now HF again this again attacks the F minus ions, again attacks on this BF3 ions, and it will form BF4 minus and H plus. This is known as the hydrogen tetrafluorophorate 3. So its nomenclature is hydrogen tetrafluoroborate. You will know more about the nomenclature of this in coordination compound, how to name this. Just for the time's sake I am telling you it forms. So the final product is H plus BF4 minus. So hydrolysis product is the same, BOH whole thrice, but H plus BF4 plus. Now one thing can be asked about you in the hydrolysis about the rate, that whether rate of BCl3, hydrolysis of BCl3 is faster or the hydrolysis of BF3 is faster. So one thing that you have to keep in mind is what happens that B has the vacant orbital, Cl has the lone pair also. So there the back bonding, this is known as the back bonding, Cl donates his electron to boron and this is known as the back bonding. So because of this back bonding, boron is not that deficient. Same in case of BF3 also. But in this case the electrons are coming from 3p vacant 3p orbital to 2p orbital, and in this case the electrons will come from 2p orbital to 2p orbital. So the 2p orbital back bonding is stronger than the 2p back bonding. Therefore the BF3 would be, boron of BF3 would be less Lewis, I should say Lewis acid, the one which accepts the lone pair of electrons or one which get attacked is called a Lewis acid. So Lewis acid character of BF3 is less as compared to BCl3. So the order of Lewis acidity in this case would be BF3 is the least Lewis acid, then BCl3, then BBr3, and then Bi3. So this is because of that the 2p back bonding is taking place in here, which is quite good, which makes it less electron deficient. Therefore oxygen will not attack quite easily as compared to BCl3 in this case. So rate of the reaction, if rate of the hydrolysis reaction is asked to you, then it's faster in BCl3 as compared to BF3. So this is quite a good question, and many questions can be asked about the rate also and what is the final product, and about the back bonding also. The order of back bonding is BF3. Order of back bonding, if you will say, then BF3 has the highest back bonding, then BCl3, then BBr3 and Bi3. This is the order of the electron deficiency of the boron. That is, the boron of BF3 is least electron deficient, then BCl3, then BBr3 and then Bi3. Yeah. So next question is that we know that AgCl is colorless but AgI is yellow in color. Why is that? So because of that, you know the polarization, that covalent ionic character in covalent character in ionic compound, Fajan rule. So I have told you one concept in that that more the size of the anion, more will be the polarization of the anion, and more will be the polarization, it is easier to partially excite the electron of the anion, and that's why the electron of AgI gets excited easily, and when they come back from the excited state to the normal state, they radiate the radiation in the visible light spectrum. That's why AgI is yellow whereas AgCl is colorless. So that was the question number 3, or I should say that was just a mere explanation of a fact which these questions have been asked frequently. So question number, I should say, 4. Question number 4 is write the Lewis dot structure of the nitrite ion. So first we have to determine what is the nitrite ion. Nitrite ion is NO2 minus. So commenting on the nitrite ion, it is NOO. This would be said as the skeletal structure. We have just drawn the ions which are present, the skeletal structure. Now this has 2 lone pairs, and this is sharing its 2 electrons with this nitrogen, and this has 3 lone pair and it is sharing 1 here, and this whole has the charge minus, and this again itself has 1 lone pair. So you can see here that octet of every atom is complete. This is complete, this is also complete, it is also having 8 electron, it is also having 8 electron, and this also is having 8 electrons. This is the Lewis dot structure for NO2 minus. This is not a odd electron species. The electrons is 7 plus 16 plus 1, that is 24. If it is an odd electron species, then the octet rule will not be applied. So if you try to replace it with the bond structure, what would it be like? It would be something like N, O has, and this is double bond O, and O oxygen will have the negative charge. So what is another possibility? That this bond comes here and this bond gets shifted, then the next charge would be oxygen minus, this is single bond, this is N, this is double bond, and this is oxygen. So these are the two resonating structures, as you can see, that, and the stability of both are the same. These are the two resonating structures. The final structure would be something like N, single bond O, not double bond character in its, and some double bond character, and whole charge minus 2. So if you want to calculate, whole charge minus 1. So if you want to calculate the bond order of this, since the stability of both the resonating structures are the same, therefore we can apply that bond order would be equals to total number of bonds involved in the resonance, that is 3, divided by the total number of resonating structure, that is 2, that is 1.5. So bond order would be 1.5. So if a question comes that in NO2 the bond length of both NO bonds have to be experimentally determined to be equal, and they lie between, they are smaller than the double bond but the greater than the single bond. How will you explain like this? You will explain is using this bond order, because it is 1.5, since bond order is inversely proportional to the bond length. So the bond length of the single covalent NO bond would be greater than this NO covalent bond, but it would be less than it would be greater than the double NO covalent bond. Okay. So next would be, if you want to comment on the bond angle, you are given some structure, some molecule, and you want to comment on the bond angle, how the bond angle can be determined. If you are given some molecules and you have to comment on which has the largest bond angle or something like this. So let's say we have 4, this is question number 5. We have 4 compounds, CO, F2, 3 bond pair, no lone pair, sp2 hybridization, and trigonal planar. The same applies for the COCl2, COBr2, and COI2. So you have to compare this bond angle theta between the XOXCX bond, XCX angle, where X is a halogen. So in this case, double bond will have some repulsion with this single bond, and it will contract this, it will lead to this contraction or diminution of this angle. So it would be definitely less than 120 degree in case of F. Now the order is, the bond angle in this is least, this is least, this is least. Now there are 2 explanations to explain that. The first explanation would be something like that because as we are going in this order, the size of the halogen is increasing. So because of the size of halogen is increasing, there is steric repulsion between these 2 atoms. Because of that, this bond angle is expanding. Therefore the bond angle is greatest in this COI2, then in COBr2, then in COCl2, and at least in COF2. The other explanation would be something like this, that since F is the most electronegative, so the negative charge most of the time resides here, and the delta plus here would be less. So the most of the time the electrons of this bond would be something in this half. So it would be easier for the shared electrons to contract it. However, as we go here, since the electronegativity of the halogen is decreasing, so the electrons which are lying in the left half of the CF bond now will oscillate more as we come here. So there would be a less, there would be some electronic repulsion between this bond and this bond pair. Because of that, this angle theta 1, it would be greater than theta, and same applies for the others also. So these are the two explanations. Any explanation you can use for this. Yeah. So same thing you can apply in, let's say, OF2, OCl2 and OBr2. We know that it has two lone pairs, so two lone pair, two bond pair, sp3 hybridization and V shape. So two lone pair here also, two lone pair here also. So in this case, again because of steric repulsion, the bond angle is in this order, and this bond in the steric repulsion is so high that this angle is in fact greater than 109.5 degree, which should not be the case, because in tetrahedral the ideal angle is 109.5. So it overcomes this lone pair repulsion. This is steric repulsion overcomes this lone pair and this lone pair bond pair repulsion. So you can imagine what is the contribution of steric repulsion in this case. To be experimentally, it is determined it is 111 degree, and in this case it is greater than 111 degree, and this is 102 degree. Comparably, fluorine is a very small element in size as compared to chlorine and bromine. So in this case, the lone pair and lone pair bond pair repulsion is quite dominant over this steric repulsion. Or in fact, I should say there is no steric repulsion in case of OF2, but there is a significant steric repulsion in case of OCl2 and OBr2. So these were some questions on commenting. If you are asked about the comparing the bond angles, then you have to keep in mind the steric repulsion also, not only the lone pair bond pair repulsion and lone pair repulsion, in fact steric repulsion also. So question number 6, and this is objective question because we are preparing for JEE and JEE is now objective. So in meanwhile I will also take objective questions. So it is said that you are given pH4 plus, H3S plus and NO2 plus, and you are asked which of the following is linear in shape. So what are the possibilities? What should be the hybridization to be the linear? So most of the students just recognize that it should be sp hybridized, or I should include one more, XeF2. So it is more than one, correct? So let's say most of the students just recognize that it should be sp hybridized for the molecule to be linear. So they just look at this, they say it is sp3, this is again what you can say 3 plus 1 sp3, this is again sp, and this is sp3 d2. So definitely only this would be linear, but they forgot the case in which the hybridization is sp3 d2, sp3d, in fact not sp3d2, sp3d, and in which there are 3 lone pairs. So in that case what happens? In this case, if the element is let's say AB2E3, then it would have the structure something like this: A, B, B, lone pair here, lone pair here, lone pair here, and this is also linear in shape. So this is one thing you have to keep in mind, that the sp3d having 3 lone pair and 2 bond pair is also linear in shape. Again for sp hybridized obviously linear in shape. This is the thing that most of the students miss. So this is a good point to keep in mind, that whenever it is asked the linear, you just don't look at the hybridization only, you should look at the structure also. So when you will draw the structure of pH4 plus, it will be something like this: pH, H, H, positive charge on phosphorus, so it will be 4 bond pair, no lone pair, sp3 hybridized, tetrahedral. For S3S plus, what would be this? It would be S, H, 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 1 lone pair, so it would be 3 bond pair, 1 lone pair, sp3 hybridized, steric number 4, and it would be somewhat what you can say bent in the geometry or in the shape. NO2 plus, if we are saying about the NO2 plus will have this, that is 2 bond pair, no lone pair, sp3 hybridized, so it will have the linear in shape. And XeF2 will have 2 bond pair, 3 lone pair, so it is sp3d hybridized, and it would be the type of AB2E3, and this is also linear. So these are the 2 compounds which are linear in shape. So always keep in mind this type of this type of molecular type also, because this is also linear in shape. So this is actually an important example. It can be asked in more than one correct options, and that which of the following are linear in shape, and if you are given an example of molecular type AB2E3, then you have to click that also. Another question is again the objective type, that it has been, you have been asked about the O and O angle, that is bond angle also. So you are given the O and O angle is maximum in the first option is NO3 minus. NO3 minus. So what would be happen? N double bond O would be something like this structure, but you will see that it's not completing, so we will do like this. So this is the structure for NO3 minus. So it is having no lone pair, because this lone pair is related to this, and 3 bond pair, so sp2 hybridized trigonal planar. But because of this double bond single bond repulsion, this angle would be greater than 120 degree and this angle would be less than 120 degree. Again, there are few resonating structure of this. You can just shift it from here, or if you want to replace this coordinate bond by positive or negative, so there would be, I think, 3 resonating structure, 4 bonds, so bond order would be 1.33, as all the resonating structures are of equal stability. Again, the next is NO2 plus. As we have said that NO2 plus is this, so its angle is 180 degree. I think the angle cannot be greater than 180 degree, so I think most probably answer would be B. But let's look at the other options also. Other is N2O4. So N2O4 is N2O4 have a single bond also, a single bond between this and this O. There is double bond, this is a single bond, double bond, there is a single bond. So again, this O and O angle, this is sp2 hybridized. So this angle would be obviously greater than 120 degree, but since it is objective, we don't have to compare all that bond, because it would be difficult to compare between this and this, that O and O bond is greater in this or this. So we don't have to compare that. So we can definitely say that it would be less than 180 degree. So our answer is it's still B. And the last option is NO2, which is something NO and this. This is the structure of NO2, and definitely this is also, this will have one lone pair also. So this is not the what you can say 180 degree. It is less than 180 degree. In fact, it is experimentally determined to be 134 degree. 2 lone pair, 1 bond pair. Sorry, 2 bond pair, 1 lone pair, sp2 hybridized. However, it would be bent in shape. So this is how. So the answer would be B, NO2 minus. NO2 plus, in fact I write this minus, this is NO2 plus. So this is how you will predict structures. So I think we have done few questions on bond angle, how to comment bond angle, because I have not taken much illustrations in the basic level. So I tried to take as much illustration possible on bond angle, because it has questions on bond angle have been asked in JEE for quite a time in previous years. Yeah. So next question is the it's a subjective question. The triiodide ion, that is I3 minus, exists and is stable, but F3 minus ion does not exist, or you can say it is not stable. That is why. Why is this? Because I3 minus can have the expanded octet, because I have vacant d orbitals present here. But as far as the fluorine is concerned, there is 2s and 2p. There is no d or vacant orbital, so it cannot have an expanded octet, and therefore F3 ion minus ion doesn't exist. Next question is that again an objective one, that which of the following species are diamagnetic. So again I will recall what do you mean by diamagnetic. Diamagnetic would mean that there are no unpaired electrons, and paramagnetic would mean that there is at least one unpaired electron. So first example is C2. So whenever you see something like that and you have to comment on diamagnetic, or whether a species is diamagnetic or whether a species is paramagnetic, you must recall a molecular orbital theory, MOT, because this is how we can predict its paramagnetic nature or diamagnetic nature. So if you will say about the C2 number of electrons, in C2 would be 6 plus 6, 12. So it would be something like this: sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Now the number of electrons is less than 14, therefore the next electron will go into pi 2p x2, and other 2 will go in pi 2p y2. So it is in fact diamagnetic because all the electrons are paired. The next is O2 2 minus. So O2 has electrons 16 and 2 minus will make it 18. So there are 18 electrons we have to fill. So it would be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, and its molar number of electrons is greater than 16. Therefore it would be sigma 2pz2, then it would be pi 2px2, pi 2py2. So how many electrons we have filled? 8 and 14. 14 electrons we have filled. We have to fill 4 more electrons. The next would be pi star 2px2 and pi star 2py2, since these both are equal energy levels. So this is also again the paramagnetic species. So if you will comment about the bond order of this, you will say it will have a bond order of half of number of bonding orbitals minus number of anti-bonding orbitals. So it would be the number of bonding orbitals are 4 plus, or this cancel out each other, there are 4 in fact, 4, so the C2 has a bond order of 2. So one thing to note here about this, that there is no sigma bond in these two orbitals. The bond order 2 indicate that both bonds present are of the nature pi bond. So this is something very different as we have observed from the valence bond theory, because valence bond theory says that if there are one pi bond present, then there would be one sigma bond present also. But in this case, it has the bond order 2 and both the bonds are pi bonds. So this is a thing that you have to notice, a very good thing, because it can be asked in J straightforward. Then C2 has both the bonds present of 1 sigma 1 pi to the both pi. So if you will not apply MOT, you will just say 1 sigma and 1 pi, but that would be incorrect. In case of O2 2 minus, the bond order would be half times. So this cancel each other, and I should say this cancel each other. Only these two electrons are the one whose anti-bonding orbital is not present. So it would be 1, and you can say that this one orbital will be the sigma bond. So this is also diamagnetic. So this would be chosen. This is also diamagnetic. This would be chosen. Bond order of C2 is 2. Bond order of O2 2 minus is 1, and the C option is Li2. So Li2 has 6 electrons. It would be sigma 1s star, sigma 1s2, sigma star 1s2, and sigma 2s2. So it is also diamagnetic in nature, and it has the bond order of 1. The D option is N2 plus. So N2 plus has 13 electrons, because N has 7, 7, 14 minus 1, 13. So it would have sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, and since its number of electrons is less than 14 or less than equals to 14, so there it would be pi 2px2, pi 2py2. We have filled, I think, 12 electrons, and 1 electron will get entered into sigma 2pz1. So this species is paramagnetic because it has 1 electron. Then its bond order would be equals to half. These cancel each other, and there are 5 bonding orbitals. So in exceeding to that of bonding, exceeding the anti-bonding electrons, so there its bond order is 2.5. So this is how we determine the bond order. I also determined the bond order of each of the species, and also said that so the answer would be A, B, C, that these 3 are diamagnetic species, and N2 plus is a paramagnetic species. So this was the question number 9, and which was checking your concepts of MOT, and if you are able to write the electronic configuration according to following the MOT rules. So one very I should say important thing to note, that was of C2, that C2 has both bonds, bond order 2, and both bonds are pi bond. Okay, so next question would be again determination of bond order, you can say in 14, example question number 11. So the question is, which of the following species have a bond order of 3? So ultimately of 9 of them we were just considering B2, C2, N2 plus, something like that. Now we will consider heterogeneous species. By heterogeneous species I would mean something like CO. So CO has electron 6 plus 8, that is 14. It has a number of electrons 14. So it would be sigma 1s 2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2, pi 2py2, and sigma 2pz2. So the number of bonding minus number of anti-bonding orbitals are 6. So half into 6 would be equals to 3. So this has the bond order of 3. CO has bond order of 3. The B option is Cn minus. Cn minus again has 14 electrons. It will have the same configuration, so it will also have the bond order of 3. The third option given is NO plus. NO plus has 15 electrons. So nitrogen would be 8 plus 15. So sorry, 7 plus 8 minus 1. So it would be 14. So this will also be there. And the last one is O2 plus, which I think will have the bond order of 2.5, because O2 is paramagnetic in nature and its last electron enters into the antibonding orbital of pi. Therefore, the one will be, it will be removed, it will be have the 2.5, so this will not be in there, and the answer would be A, B, C, CO, Cn minus and NO plus. These three species has the bond order of 3. Right? So these two questions were based on the MOT and writing the electronic configuration and commenting on the bond order or bond length. You can also comment on bond length also, or stability of molecule. More the bond order, more would be the stability of the molecule, and bond order is inversely proportional to the bond length. So next question is the correct order of bond energy. That I was talking about bond energy. So next question is correct order of bond energy. So we have to compare, I just will write what we have to compare. We have to compare N2 minus, N2, N2 plus and N2 2 minus. So we have compared that N2 has 14 electrons and it has bond order of 3. N2 minus, the one electron will enter in the anti-bonding orbital, because all the bonding orbitals are filled. It will be entered in the pi 2p x. So it will have the bond order of 2.5, since the antibonding electron increases by 1. And then 2 plus, the electron will be removed. There are 13 electrons, and electron will be removed from the sigma 2pz. So it will be removed from the bonding orbital. So it will also have 2.5 bond order. And N2 2 minus will be, this means that there are 2 electrons entering. So one electron each entering in the pi 2px star and pi 2py star. So it will have the bond order of 2. So more is the bond order, more would be the stability. So stability order would be N2 greater than N2 minus, that is equal, its stability is equals to N2 plus, and this is greater than N2 2 minus. And I think this in turn, one thing to note here is that this would be, you should say this should be the answer. But one thing in that case, that when the bond order comes to be same, then we say that the molecule having less number of antibonding electron will be more stable, because less number of electrons are in the higher energy state. So in this case N2 plus, there would be less number of electrons, so it's my words to say that N2 plus, that would be greater than the N2 minus. So this is a very good question, because you can be decepted as I was decepted, because 2.5 bond order is same, you will say their bond energy would be the same. However, it is not the case. If the bond order is the same, then you have to look at the number of antibonding electrons. If the molecule which has the number of antibonding electron less will have the more stability as compared to the other. But always notice that the number of antibonding orbitals is always the second priority. The first priority would always be bond order. If bond order comes out to be same, then you have to look at the number of antibonding orbitals. So this is a very good question, in fact, on the MOT about the bond energy, how to predict the bond energy order. Yeah. So next question is on the dipole moment, that you have NH3 and you also have NF3. So NF3 is more, the NF, you will say the NF bond order, NF bond has more dipole moment as compared to NH bond, definitely, because N has the electronegativity 3, F has the electronegativity 4, this has again 3 and this has 2.1. So the difference in electronegativity of the NH bond is less than the difference of electronegativity in the NF bond. So definitely the dipole of the single covalent bond of NF bond is greater than the dipole of the NH bond. But it is observed that the NF3, the dipole moment of the NF3 molecule is less than as compared to NH3 molecule. So what would be the reason for that? So first I will say what is the hybridization N, H, H H, 3 bond pair, 1 lone pair, sp3 hybridization bent in shape. NF3, 3 bond pair, 1 lone pair, sp3 hybridization bent in shape. So the dipole moment, the direction for the NH would be in this direction. For this it would be this, and this it would be this, and this again would be in this direction, because lone pair is obviously more electronegative in there. In this case it would be this, in this case it would be this, this and this. So because of this, the resultant of these 3 NF bond is opposite to this dipole moment of N lone pair. However, in this case, the resultant of these 3 NH bond is in the same direction as compared to this dipole moment. So if you will ask that, and also the difference in the dipole moment of the single covalent bond is not much, because here the difference is 1, here the difference is 0.9. So definitely this will cancel out, not completely cancel out, or I should say minimize the effect of this single dipole, and therefore the dipole moment of NS3, mu NS3 is greater than mu NF3. And you will know that the dipole, the unit of dipole moment is dBi. So this was the application on the dipole moment. The next question I'm taking is on the solubility. So how will you say the solubility? So the question is that the ethylene, that is C2H2, is not soluble in H2O, but it is highly soluble in acetone. Why does this happen? So C2H2 is something like this: C triple bond C H H, and H2O would be H2O would be H O O. Now we know that the H2O is itself bonded in itself. So this lone pair of this oxygen is bonded to the hydrogen of other water molecule by hydrogen bonding, that is intermolecular hydrogen bonding taking place between the 2 molecules of the water molecule. So this lone pair would be not readily be available for the hydrogen bonding to this hydrogen. So that's why the hydrogen bonding will not take place, and its solubility is very less in the H2O. But in case of the acetone, that is the CH3COCH3, this oxygen is completely available for the hydrogen bonding. This is delta plus ion. It is sp hybridized. So sp hybridized with 50% s character, so highly electronegative as compared to sp2 hybridized carbon or sp3 hybridized carbon. So it is delta plus here, and there will be delta minus charge here, and this will show hydrogen bonding because this has 2 lone pairs which are completely localized on this oxygen atom only. However, in this oxygen atom it was not localized, it was delocalized to others because it was also bonded to the hydrogen of other water molecule. So that's why it is soluble in acetone. However, it is not soluble in water. Ethylene is soluble in, this is ethylene is soluble in water, and this is acetone. You will learn more about these compounds in organic chemistry. This was question number 14. The next is question number 15. So the question number of 15 is that the tetramethyl ammonium hydroxide, that is tetramethyl ammonium hydroxide, what would it mean? Tetramethyl would mean there are 4 group of methyl group. Tetramethyl ammonium hydroxide would mean that the ammonium ion is NH4 plus. So when we are saying the tetramethyl ammonium, then each hydrogen is replaced by the one methyl group. So tetraammonium hydrogen oxide, which would mean this, so it would be something like NH3 plus and OH minus. So tetramethyl ammonium hydroxide is a stronger base than that of tetramethyl ammonium hydroxide. So the thing is, another one is trimethyl. So it is CH3 and one H group is there, and it is OH here. So it is said that the tetramethyl, this one, is a stronger base as compared to this one. Why will this happen. First, what is the base? The base is the one which can provide electron or which itself get oxidized and reduce other. So when we are talking about the base, we are talking about the Lewis base character. So we have to compare on the Lewis basicity of this ion and this ion. So when we are talking this, so N CS3, I'm drawing it something like this, but it would be obviously tetrahedral in shape because it is sp3 hybridized, and it would be CS3 here. So this lone pair, this lone pair, and this is OH minus ion. So nothing is. But in this case, what happens that it has CS3 here, CS3 here, CS3 here, and this is a hydrogen atom which can form an hydrogen bond with the oxygen OH minus ion, which will have a high negative charge or full negative charge on it, and the delta plus. So this hydrogen bond is formed in this trimethyl ammonium hydroxide. However, there is no such interaction in the tetramethyl ammonium hydroxide. Therefore, it's delocalized, or that's why it is more basic in structure. Because OH minus ion is linked with this. OH minus ion is linked with an extra attraction, hydrogen bond with hydrogen. So it's difficult for it to ionize into OH. More energy would be provided to ionize into OH. Therefore, it is a weaker base as compared to tetramethyl ammonium hydroxide. This is trimethyl ammonium hydroxide. Okay. So these were some questions. Question number 15. Now talk about the one more thing. Next is the structure I was talking about in the basic level. I talked about the 3-center 2-electron bond, and I took an example of BS3, I think, in the dimer form. BS3 forms an tetrahedral, or I should say 3-center 2-electron bond. So BES2 is one more species which forms this 3-center 2-electron bond. It is something like this, that BE is here, H is here, then there is H, but it's all in the dimer form. This is BE here, there H here, and this is in solid form also. So it's solid, not in gaseous form. If it is in gaseous form, then it will definitely be linear in shape. And this is H. So this forms a 3-center 2-electron bond. That is, this 2 electrons, or their 2 electrons are delocalized over 3 atoms. So this is and also known as the banana bond, you can say. So something like this. So 3-center 2-electron bond, or I should say banana bond. One more example for this is Al2CS3 6. So aluminium, one CS3 here, one CS3 here, and there is another aluminium, one CS3 here, one CS3 here, and then these 2 electrons are distributed over or delocalized over 3 centers. So again, this also forms a banana bond, and this also forms a banana bond. So these 3 can be asked, that BS3 and BES2 in solid and Al2CS3 6 forms this banana bond. However, the same is not the case with Al2Cl6, because Al, Cl, Cl in dimer, if you will say, and again a Cl, and here it is Al, Cl, Cl, Cl. So it is forming a coordinate bond, and this is also forming a coordinate bond. So definitely its bond length would be greater than as compared to this bond, but this bond length would not be same of this bond and this bond. But it is not a 3-center 2-electron bond. It is 3-center 4-electron bond, or we can say the normal covalent. This is covalent bond, and this is dative bond or coordinate bonds. This was one structure which I want to discuss here also. So yeah, the next would be my illustration on the back bonding, which I have explained you what is a back bonding, that 2p back bonding and 2p3p back bonding, that BF3 has the p pi back bonding, as the BCl3 also have BBr3 also has the 2p back bonding, and BI3 also has that, but the extent of back bonding is greater in BBF3 than in BCl3, than in BBr3, and then in BI3. So let's move on to the next question, question number 16. So the question is that we have two compounds SiH3NCO, and another one is one is SiN3H3O, another is CH3NCO. So it is said that this is trigonal planar in shape, but this one SiH3NCO is linear. How is this? To explain this phenomena. So let's first draw the structure of this. So it is NCO, or it is SHH. This is something like this, and this is N double bond C double bond O, and then carbon again, and this is H. So this is also known as the silyl isocyanate, and this is also known as the methyl isocyanate. This is an isocyanate group. NCO is an isocyanate group, and CH3 is a methyl, so its naming nomenclature is methyl isocyanate. I should not say nomenclature, its common name is methyl isocyanate, and this common name is silyl isocyanate. So this is the structure. So you can say one bond pair, two bond pair, one lone pair, sp2 hybridized. They're definitely trigonal planar. I should not trigonal planar geometry. By this would I mean that it is something like bent or something like this. Now, why this is linear? What can be the cause of the silyl isocyanate to be the linear? It also has this lone pair, but one thing to notice is that the silicon atom has the vacant 3d orbital. So it can donate its lone pair into the vacant 3d orbital and form a p pi d pi back bonding. So this is the back bonding example, that it's p pi d pi. It would be something like this. This is p orbital, and this is the d orbital. So it would be this density, and this density will overlap, and in here this density and this density will overlap. So this will form the p pi d pi back bonding. Because of that, this comes in this lone pair is no longer localized, it is delocalized, and which turns it into the sp hybridized, or I should say its shape becomes linear. However, the carbon has no such vacant d orbitals, therefore its shape is its hybridization is still sp2, and shape is bent in shape. So that's the reason, that's why the SiCH3 or silyl isocyanate is linear in shape, whereas the CH3NCO is bent in shape. Not trigonal planar, it should be bent. So this was the question number 16. Simple illustrations, but you just keep in mind all the all the topic, that is back bonding when you have to apply back bonding, when you have to look for the bond length, how to compare bond length, and how to compare all this stuff. Yeah. So next question, that is question number 17, would be the ionic radii, comparison of ionic radii and about their mobility. So we are given Be plus 2, Mg plus 2, Ca plus 2, beta mangika scooter. That was for the alkaline earth metal. I have learned that in periodic properties, that if you want to learn about the alkaline earth metal, the remember would be beta mangi car scooter ba proe. So it is beryllium, magnesium, calcium, strontium, barium, and then radium. However, we don't talk about the radium. So Sr plus 2 and another one is Ba plus 2. So if you want to compare on their ionic radii and in the water and their mobility also. So we know that more smaller the cation, more heavily it would be hydrated, more H2 will try to get attached to it, because more smaller the cation, more would be the concentration of positive charge, and more would be the inner pull of electron towards this Be plus 2. So because of this, many hydrogen gets attached to beryllium as compared to magnesium, and the heavily hydrated ion now Be plus 2, which was smaller in size, if you will say about the solid or gaseous state, if you will say in fact gaseous, if you will say about the gaseous state Be plus 2 or solid state Be plus 2, it would be smaller in size than the Ba plus 2. But when you are talking about the aqueous form, when you're talking about that, it is hydrated, so this is greater than this is greater, this is greater. So this is the order of ionic radii of Be plus 2 of the alkaline earth metal divalent cation when they are hydrated. So the electric mobility, more hydrated the cation would be, more bigger the size of the hydrated cation, less would be its mobility. So opposite is the trend for the electric mobility, that is Mg plus 2, Be plus 2 is less than Mg plus 2 is less than Ca plus 2 is less than Sr plus 2 is less than Ba plus 2. This is the order for electric mobility, and this is the order for ionic radii in water. So just apply a few concepts and you can get answer. These types of questions are only asked in the JEE, or I would say much simpler than this, not tougher than this. You have to just apply concepts, and you can say that since it is the most scoring subject, it comes around about 12 or 15 marks every year. So out of 180 of the chemistry portion applied, assigned, 12 or 15 marks can have a lot of weightage, you can say. So next question is question number 18. Question number 18 is that out of MgCO3 and ZnCO3, which one is more stable? Now for stability, you can say that a stable compound would mean that it doesn't want to dissociate, or it is stable in its present form. If it readily decomposes into some other byproducts, then it is not as stable as the other one. So here Mg plus 2 is there, and here Zn plus 2 is there. So we know that while talking about the Fazan rule, I talked about the pseudo inert gas configuration. So here Zn plus 2 possesses the pseudo inert gas configuration because it has the configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. So this is pseudo inert gas configuration, and it is possessing inert gas configuration. So in that I have said that the cation having the pseudo inert gas configuration would possess more covalent character as compared to Mg plus 2. So it will be more polarizable. It will attract the ion. It will more its polarizing power is greater than the Mg plus 2. So Zn plus 2 cation in this, and CO3 minus 2 minus here. So it polarizes this O minus ions and readily decomposes this. Oxygen comes here and this comes out, and these two combine and forms ZnO plus CO2, decomposes quite readily. So therefore MgCO3 is more stable as compared to ZnCO3 because of this polarizing power. So you know that this concept, pseudo inert gas configuration, if you don't know about this concept, you cannot comment on the stability order. So every concept has some importance, and question can be asked in JEE because this part has never been touched about the Fazan rule, about comparing Fazan rule on the basis of pseudo inert gas configuration. So it is quite an important, or I will remark it as an important question as far as JEE preparation is concerned, because it is quite a different concept and it has never been asked in JEE before. So it has high probability that it will be asked in the coming JEE years. So I will term this question as an important question. Yeah. So next question is again an objective question, that is question number 19. Question number 19 would be that you have to comment on the Lewis basic, you have to compare the Lewis basicity of the, so you are given strongest Lewis base you have to comment on. So first example is CH3CN, the second option given is CH3NH2, the third is N2, and the fourth is, or D is none of these. None of this, not would be recommended, none of this. So CH3CN, what would be its structure? It would be something like this: CN, this is methyl cyanate, isocyanate would be NC, and cyanate would be CN. So this would be CH3H. So this would be structure of the nitrogen. Here in this it would be CH, H, N, H. So it is sp3 hybridized, 3 bond pair, 1 lone pair, sp3 hybridized, bent in shape, and this is sp3 hybridized, however it is tetrahedral in shape. This N2 is N. This is, so this is sp hybridized, this nitrogen is sp3 hybridized, and this is sp hybridized. So we know that as the S character increases, the electronegativity of the element increases. So more electronegativity of the element, it would try to retain the lone pair, or the electrons try to attract the electrons towards itself. So this also is lone pair, these two also has the lone pair. However, since it is sp hybridized, so lone pair is quite stable on N, so it don't want to donate its lone pair, so it is a weak Lewis base, I should say, weak Lewis base. In this case, since it is sp3 hybridized and its electronegativity, this nitrogen electronegativity is quite less as compared to this, so among these two, this will be the stronger Lewis base. Stronger Lewis base, and the same applies for this. Since this is also sp hybridized, it don't want to donate. It has two lone pairs, but still it don't want to donate its electrons, so it would be again weaker Lewis base as compared to the CH3NH2. Therefore, the answer would be B, that is CH3NH2 is the strongest Lewis base. So Lewis base, question can be asked on the Lewis basicity and the Lewis acidity also. You have to compare the Lewis basicity and you have to look at the hybridization of the compound having the lone pair and whether it want to donate. Whenever we are asking about the Lewis basicity or Lewis acidity, you just have to focus on the hybridization of the element possessing lone pair, because then only it is Lewis base. If we are talking about the basicity or the acidity of the acid, then it can be the negative charge also, that you have to look at the other interactions such as hydrogen bonding, as we looked into the trimethyl ammonium hydroxide and tetramethyl ammonium hydroxide. In that case, because of the hydrogen bonding, the basicity of one was less as compared to others. So in that case, we are talking about the basicity. In this case, we are talking about the Lewis basicity. So that's the difference between the basicity and the Lewis basicity. Whenever we are talking about the Lewis basicity, you have to compare the element which possesses the lone pair. Yeah. Next question would be the question number 20. It's again an objective question for you have to pick incorrect statement. For statements are given to you, so I will take each statement one by one. So the first statement given is that in CF2 double bond CF2 molecule, all the four fluorine atoms are not in the same plane. This is the statement that all the 4 fluorine atoms are not in the same plane. So just look at what would be the hybridization. So it is C, this would be double bond C, this is one fluorine atom here, this one fluorine atom here. Now let's say it has inverted. So this will have, draw something like this, fluorine here and fluorine here. Why I am drawing this? This represent, you will learn in organic chemistry, or I should say in that isomerism or something like that. This represent above the plane and this represent below the plane, because these two I have drawn one less than, I think, so I should edit this, and this is something like C, F and F. So if Px is this has S, Px, Py and Pz, this Cs, this orbital. So let's say this is S and this is Px, then definitely the orbital involved in this would be Pz, and this Pz, because of this, these two planes, these two pi bonds are in perpendicular plane to each other. That's why one fluorine atom, if I consider this as the plane of these two fluorine atoms, then this fluorine atom would be above the plane and this fluorine atom would be below the plane or inside the board. It is coming outside the board, this fluorine atom is going inside the board. That's why this statement is correct, that all the 4 fluorine atoms are not in the same plane. Second statement, the second statement says that the Ka2 of fumaric acid is C2H2 COOH whole twice trans C2H2 COH whole twice is fumaric acid. So these are very common acids, so you have to just keep in mind their structure, or I should say their at least their molecular formula. So this is fumaric acid and C2H2 COOH whole twice cis form is malic acid. So I have talked about the cis and trans form. Trans is when they are opposite to each other and cis when they are on the same side. So Ka2 would mean that second hydrogen, when we are removing the second hydrogen from this ion, it is difficult. Ka2 of fumaric acid is more than the Ka2 of malic acid. That would mean that it is difficult to remove the second acid. It is easier to remove, in fact, the second hydrogen from here as compared to second hydrogen from here. Just look at we just look at the structure and we will comment on that. So yeah. So the structure of, if you want to draw the structure of the fumaric acid, that is trans C2H2 COH whole twice, it would be since it's a trans, so it would be C H here, and C O O H. This would be the structure, and the another C O O. And since we are considering about the K, comparing the Ka2, so just removing one hydrogen from here. So this is the structure of fumaric acid or trans C2H2COH whole twice. Another is cis fumaric acid, cis acid, that is malic acid. So it would be H. This is C double bond O minus, so to say, and this is C double bond O H. So now you can see that there is an interaction between, that is hydrogen bonding. It is forming 1, 2, 3, 4, 5, 6. 6-membered ring, which is quite stable. 5 and 6-membered rings are always very stable. So it is forming intramolecular H bonding. So that's why, because of this H bond is because of this interaction of H bonding, it is not easy to remove this hydrogen. However, in this fumaric acid, there is no such extra interaction, so it is easier to remove this hydrogen from the fumaric acid as compared to that of the malic acid. Therefore, the Ka2, which represents the ease of ionization or ease of the removal of hydrogen of Ka2 of fumaric, is greater than, or I should say Ka2 of fumaric is greater than the Ko2 of malic acid. So this statement is also correct, that the Ka2 of fumaric greater than Ka2 of malic acid. So it represents the intramolecular H bonding. So you have to keep in mind also the structure and also the concept of H bonding. So we have considered the two statements, and both the statements correct. The third statement is that the OO bond length in O2AsF4 is longer than KO2, than the O2 in KO2. So first, this has the term O2 plus AsF4 minus. This can be written like this, and this has a K plus O2 minus. So this is positive and this is O2 minus, that is, it is a peroxide ion, and this is superoxide ion of oxygen, and this is, you can say, the O2 plus. So if you consider about the bond order, the one electron in this case is removed from the anti-bonding pi orbital, so its bond order would be 2.5, because the normal O2 has the bond order of 2, and this O2 minus, the one electron has been added to the anti-bonding pi orbital, pi to px. Therefore its bond order will decrease, as since the number of anti-bonding electrons has increased, so its bond order is 1.5. So the statement was that the bond length, OO bond length in this is greater than that in the case this, but we know, since the bond order is directly inversely proportional to bond length, and the bond order of O2 plus is greater than the bond order of O2 minus, therefore the bond length of O2 plus indeed is less than the O2 minus, the bond length of O2 minus. Therefore the statement that the bond length of O2 plus AsF4 minus is greater than the K plus O2 minus is incorrect. So C is incorrect statement, so we have to take this also. So just consider the D statement also. So D statement says that the bond angle order in halogen as halogen. So bond angle order in halogen as halogen is SOF2 less than SOCl2 less than SOBr2. This we have considered earlier. It has sp2 hybridization, trigonal planar. We have considered that in this case steric repulsion come into picture. Therefore this angle increases quite considerably, and this angle is quite less. So this order is also correct. So D is correct. So we don't have to choose that. So the answer would be C. That is, the bond length of O2 plus ion in O2AsF4 is less than the bond length of K plus O2 minus ion. So this is the correct statement. The reverse was given to us. Yeah. So this was the question number 19. Now let's move on to the next question, that is question number 20. Yeah. So question number 20 is that we are given some data. It's a numerical question. It is an objective question, but in itself is a numerical question. We are given the lattice energy of AlCl3. Lattice energy of AlCl3 is given as is given as 5137 kilojoule per mole. Here this means that you have to provide 5137 kilojoule per mole of AlCl3 to break it into completely Al plus 3 gaseous and 3Cl minus ion gaseous. And hydration, heat of hydration of Al plus 3 is given as minus of 4665 kilojoule per mole, and the heat of hydration of Cl minus is given as minus of 381 kilojoule per mole. So this is the anhydrous AlCl3. So you are given with anhydrous AlCl3, you put it into water, and you have now to comment whether it would break into constituents ions or it would remain the same, or either Cl minus would break or something we have to comment. So first we just calculate what is the equation that we have to consider. The equation that we have to consider is AlCl3, which is in the solid form, has to go to Al plus 3 aqueous form, that is in water because we are considering it water, Al plus 3 aqueous, and then 3Cl minus aqueous. So this is the complete reaction. So how does this proceed? That first we have to supply an energy of lattice energy, we have to give lattice enthalpy we have to provide to break up into Al plus 3 gaseous plus 3Cl minus ion gaseous, and then we have to supply heat of hydration of Cl minus and heat of hydration of Al minus for this. So it would be 3 into, because there are 3 ions. So this would be the enthalpy change for the whole reaction. So we say if the enthalpy change for the reaction, this reaction is negative, then definitely this reaction will go in the forward direction and we will get hydrated Al plus 3 and hydrated Cl minus ions. However, if this enthalpy change for this reaction is greater than 0, that it is an endothermic reaction, then this reaction will not take into place and we will get solid AlCl3 also in its aqueous solution. So just calculate the equation. Delta HF would be equals to lattice energy, which is 5137, plus delta H Al plus 3, that is minus of 4665, plus 3 into delta HCl, because there are 3 Cl minus ions, so it would be 3 into 381. So this would be equal to 1143, and which one added to 4665 will give you this 58085137, which we can say is less than 0. Therefore definitely this reaction will go in forward direction, and what you will get is the hydrated Al plus 3 ions and hydrated Cl minus ions. So the options given were it will remain covalent in aqueous solution. However, we know that it breaks, so it is not covalent, it is ionic in its aqueous solution. The second option given was the solution will consist of Al plus 3 and Cl minus. So when we are saying Al plus 3 and Cl minus, this means we are talking about its gaseous state. Since nothing is stated about its other state, it's assumed to be stated in gaseous state. So definitely it would not be in the gaseous state, it would break into the aqueous. The third option given is the solution will consist of hydrated Al plus 3 and Cl minus. Yeah, this is the correct, because it will get hydrated. This is an exothermic reaction, this will go in the forward direction. So C option is correct, and D was given as the none of these, so that is not correct because C is the correct option. So how to just if the delta H of the reaction is obviously an exothermic, it will go in forward direction by itself. You don't have to provide any extra energy for this reaction to happen. Yeah. So the question now is the question number 21. The next question is, which of the following compounds you accept to be the most ionic? So the first is PbCl2, the second is PbCl4, the third option given is CCl4, and the fourth option given is SnCl4. So this all belong to the carbon family, which is Consi, Gita, Sneha, Prabha. So this was how I remembered it. So the option given is not Sn, it was SiCl4. So this is the thing. So you have to predict the most ionic character. So commenting on the ionic character, more small the cation is, since the anion is the same in all the options. So first we have to consider the cation. So more small the cation would be, more would be the polarization done by this to the anion, and more would be the covalent character. And more would be the covalent character, the least would be the ionic character. So definitely this is the smallest cation, so this will be the most covalent. Then this would be the second one, and this would be the third one, or so to say PbCl2 or PbCl4, anyone will be the third one. Now we have to compare in PbCl2 and PbCl4 that which one is the most ionic. Yeah, we have to consider which one is the most ionic. So since the cation is same, now we consider on the anion. Since there are 4 anions, so there are more polarization done in terms, you can say in absolute term there would be more polarization done by the Pb+2 on the 4Cl ion. So there would be more covalent character in PbCl4 and there would be less covalent character in PbCl2 because there are only 2 anions here and there are 4 anions here and all the other factors are same here. Or you can say it has a +4 charge, it has a +4 charge. This is also, you can explain this is a +4 charge, this has +2 charge, more polarization, less charge, less polarization, more polarization leads to more covalent character, and more covalent character would mean less ionic character. So this would be the most ionic. So first, this is the least charge, +4 charge. From this you concluded that this should be the most ionic among this, and from these two this should be more ionic. So on all those 3, this should be the most ionic, the option A. So there are 2 concepts checked of the Fazan rule. One is the small cation, the smallest cation, the polarization is inversely proportional to the size of the cation, and one is the polarization is directly proportional to the charge of the cation. Yeah. So this was question number 21. The next question, the question number 22 would be 22 would be a subjective question, that is, explain the structure, hybridization and oxidation of Marshall acid, Carrow's acid, oleum and sulfuric acid. You might be knowing about the sulfuric acid definitely, but it is possible that you have not studied about the rest. Oleum, Carrow's acid and Marshall acid, they are very common acids, so it can directly come into the exam that comment about the hybridization or comment about the what you can say hybridization or how many bonds are there or something like this can come in the picture. So you have to remember the structure for this. So the molecular formula for the Marshall acid would be H2S2O8. The molecular formula for the Carrow's acid is H2SO5. The molecular formula for oleum is H2S2O7, and the molecular formula for sulfuric acid is H2SO4. Yeah, these are the acids. So I talked about the acidity the next day. So it has the acidity 2, it has the acidity 2, it has the acidity 2, and it also has the acidity 2. The 2 acids which have the acidity not according to their hydrogen atoms are H3PO4, which have the acidity 2, and H2PO3, which have the acidity, this has the acidity 1 and this has the acidity 2. So these are the two acids you have to keep in mind, in which the number of hydrogens is not equal to the acidity of the acid. H3PO4 has the acidity 2 and H2PO3 has the acidity 1. So it is the phosphorus acid and this is H2PO3. Yeah. So now let's talk about the structures, hybridization and the other stuff for all this. So we have to predict the structure, hybridization and oxidation state of the sulfur ion. So now you can say the one thing is that the sulfur can have the maximum oxidation state of +6. So if we, and the oxidation generally has the oxidation state -2. So if we assign -2 oxidation state to each oxygen atom, it is a neutral molecule, so the overall positive and negative charge should be equal. So oxygen, if it has a -2 charge on each, so it would provide the -16 charge. It would be, hydrogen is +2 obviously because each one has +1 charge, so +2. So this would mean the 2 molecules of sulfur should have the +14 charge, which is not possible because each one of has to be, at least one has to be the charge of 7, but we know that the +6 is the most charge which it can occupy. So definitely all the oxygen are not in the -2 oxidation state, so there is at least 1 or 2 oxygen which are in the -1 oxidation state. So the structure for this is something like this, that sulfur, there is a sulfur-sulfur bond in here, there is a double bond O, this is a double bond O, double bond O, double bond O. So these are 4, and there is a O, O, H, and O, O, H. So this is H2S2O. This is in the oxidation state -2, -2, -2, -2. But these 4 are in the oxidation state of -1. So this is one thing you have to keep in mind. And sulfur is in the oxidation state of +5. We are asked about the oxidation state also, so I am saying about all the oxidation states. So +5 oxidation state for these two sulfur, -2 for the 4, -2 oxidation state for the 4 hydrogen which are 4 oxygen which are bonded by double bond, and other 4 oxygen will have -1 oxidation state. So this is the structure for H2S2O8, and its hybridization would be sp3, 4 bond pair, no lone pair, tetrahedral geometry, and the oxidation state I have mentioned. Talking about the Keros acid, same thing you will have to apply here, that oxygen have -2, if all the oxygen have -2 charge, it would have -10 +2, so sulfur would have to have +8 charge for this molecule to be neutral. But we know that the sulfur can have maximum of +6 charge. Therefore, it should be there should be an OO bond present. Because of that, there should be -1 oxidation state on this. So it would be something like this: that double bond O, double bond O. Here it is double bond O, double bond O, H, and here it is O, H. So this is the structure for the Keros acid. So it has -2, it has -2, it has -2 also. I think it is sulfur is 2, 2, yeah, so fine. So it has -1, it has +1, it has +1, and this one has also -1, yeah. So the total charge is neutralized, that -2, it would be in oxidation state of 6, I guess. So 6 + 1 + 1, that is 8, and 2 + 2 + 2 + 1 + 1 would be 8. So the new positive charge and the negative charge are neutralized, and it would have the sp3 hybridization, 4 bond pair, no lone pair, tetrahedral geometry. This is the structure for Keros acid. So you can also someone can ask about the structure of their ions also. I can ask about the structure of HSO5 minus ion, that is persulfate ion. Then you have to remove one hydrogen from here. Definitely it would get removed from somewhere or somewhere here, and then it would. You can ask. There can be slight modification to that. I am just saying that. So just keep in mind everything. Now let's talk about the oleum. So first I have to rub these two structures because they are occupying a lot of space on this board. So I am not drawing it according to shape because it would be quite difficult for me to draw on the 2D on this board. So yeah, next would be H2S2O7. So if all the oxygen will have the -2, then it will contribute -14, it will have +2, so it will have each sulfur has to have +6, and this can be possible. So in this case, what would happen, there is an oxygen bond in between SOS. So, and whenever there is rule, then whenever the number of oxygen are, you can say, odd, and the sulfur ion has its, if you assign all the -2 and the sulfur ion has the oxidation state within its range, then there is an oxygen SOS bond always. So this is a rule. There is also an exception of this rule. I will talk to you about this later. So this is SOO here. Then there is OH, then there is a double bond here, there is a double bond here, there is a OH, I think 1, 2, 3, 4, 5, 6, 7. So this is H2S2O7, 2 hydrogen. So it will have -2, it will have -2, -2, -2, +1, +6, -2, I have noted here. So it is +6, -2, -2, -2, +1. So hybridization of this would be sp3 and tetrahedral in shape, and +6 oxidation state of oleum. So you again don't get confused if it is asked about this anion. Just you have to remove one hydrogen from here, and this would be the structure for the HS2O7 minus. So this is the simple. H2SO4, very simple structure. It is +6 oxidation state. You can just calculate it from here. So it would be something like this OH here, and this OH here in the +6 oxidation state. All the oxygen are in -2 state and all the hydrogen are in the +1 state. So the rule was this: if the number of oxygen are negative and if you number of oxygen are odd, and if you assign the -2 oxidation state to each oxygen, and resulting from it, if the oxidation state of sulfur is coming to be its in valid oxidation range, then it would have always SOS bond. However, if there is something like this, that here also the number of oxygen is odd, but if you assign each oxygen -2 state, then you will have the oxidation state of +8 on the sulfur, which is not possible, we know. So then there will always be an OOH bond. So these two can be keep in mind. And if there is a number of hydrogen is even, and if it is coming in range, then also it will have SS bond, and if it is not coming in range, then definitely there would be OOH bond. So these are the few things you have to keep in mind for drawing any structure. Now I was talking about the exception for that rule, that is when the number of oxygen are odd and the oxidation state for each sulfur atom is coming to be in range, then there should be SOS bond. However, there is one acid which doesn't follow this structure or this rule, which is H2S2O5. In the H2S2O5, you can say that if the number of oxygen are odd, if you assign each oxygen -2 and each hydrogen +1, you will get each sulfur oxidation state of +4. So this is in range. So according to you, the structure would be something like this. You will say fine, this, and this. You will say this should be the structure. However, the case is this is not the structure. This is the wrong structure for this acid. The correct structure for this is that there is a SS bond in this, and we have assumed in all cases that the oxidation state of both the sulfur atoms are same. However, this is not the case in this molecule. This is double bond O, this is double bond O here, there is a double bond O here, there is a OH, and there is a OH here. OH here. So this is the correct structure for H2S2O5. One sulfur is in +3 oxidation state, one sulfur is in +5 oxidation state. It has 4 bond pair, no lone pair, sp3 hybridized orbital. It has, and shape is tetrahedral. In this case, it has 3 bond pair, 1 lone pair. So it is also sp3 hybridized since the strike number is 4, but its geometry would be bent, not tetrahedral. So this is the exception to this rule, and it can also come in exams since it is an important exception. So I will note this as an important. So just keep in mind this structure H2S2O5 and the structure for others also, because that rule is followed for all the other structure, but this is the one exception to it where it fails. The structure of H2S2O5. The correct structure is this, where one sulfur has +5 oxidation state and one sulfur has +3 oxidation state. Yeah. So that was about the acids and acidity. Now the next question, let's jump to the next question, that is question number 23. Question number 23 would be the BCl3 is more acidic than BF3. Why? I have talked about this a little bit earlier, that BCl3 and BF3, they clearly, because of the extent of back bonding in this is quite much larger as compared to extent of back bonding in BCl3, because here the back bonding involves 2p2p orbitals. Here the back bonding involves 2p3p orbitals. So this back bonding is not as good as compared to BF3. That's why the boron of BF3 is less electron deficient as compared to the boron of BCl3. Therefore, it will not accept electrons as easier as it would accept as in the BCl3 molecule. Therefore, acidity of BCl3 is greater than the acidity of BF3. So this is I have just talked about it earlier also. Just remind me of this illustration, as this is an important concept of back bonding. Yeah. The next question, question number 24, is that BF3. Question number 24 is that BF3 in gaseous state in diethyl ether. Diethyl ether would be OC2H5 whole twice. Diethyl ether forming a viscous liquid. It in BF3 gaseous in the diethyl ether forming a viscous liquid. Why does this happen? This can happen because F is here, F is here, F is here, this oxygen, then there is C2H5, there is C2H5, this has lone pair, this has back bonding. I told you about the back bonding. When we are comparing the acidity, then definitely BCl3 is more acidic than BF3, but it doesn't mean that boron will not accept the electron from hydrogen atom. It will from oxygen. It will accept electron, but it would not be as fast of the reaction as in the case of BCl3. So this accepts there is a coordinate bond, or you can say dative bond, which attacks, and boron has a vacant p orbital, it has a lone pair, so there is a bond formed, and the resultant molecule is a viscous, therefore it forms a viscous liquid. Yeah. So this was the question. So let's talk about the next question. Now I'm stepping on to the objective questions, more of objective question following the pattern of IIT JEE. Question number 25. Question number 25 would be, you have to say that there are some characteristics are given, and you have to comment which molecule will have all the characteristics. So the four options are B2H6. The second option is Al2Cl6. The C option is BeCl2 in gaseous form, and the D option given is BF4 minus. So yeah, so the first property given is tetrahedral hybridization. So B2H6, it is a dimer, we know it forms a banana bond, 3 center 2 electron bond, sp3 hybridization, it applies to this. Al2Cl6 form are located by the coordinate bond, its hybridization is also sp3, 4 bond pair, no lone pair, its hybridization is also sp3. However, BeCl2 in gaseous form have the hybridization sp, and it is a linear in shape, so definitely C cannot be the option, C cannot be the correct answer. And BF4 minus again has 4 bond pair, no lone pair, so it has the sp3 hybridization also. So from the first statement, C is ruled out. The next option is, the next property given is hybridization can be considered to be taken place because of the empty orbital. So this is also has the empty orbital, this also had the empty orbital, and this also had the empty orbital. So again, all three are the possible candidate for this. The next is all bond lengths are identical, that is all AB bond lengths are identical. So in this case, B2H6, we know that a 3 center 2 electron banana bond is formed, so that bond has the bond length, that BH bond length is greater than, that is this bond length which is formed here in the boron, and this hydrogen and this hydrogen and this H, this BH bond length is less than as compared to this boron H length, therefore this cannot be option. The same is in case of Al2Cl6, the coordinate bond formed by the coordinate bond has the bond length greater than the other AlCl bond. However, in case of BF4 minus, it has a perfect tetrahedral structure having, this would be the structure for BF4 minus, perfect tetrahedral structure having all the bond length, all the BF bond length equal. Therefore, the answer should be the D, that all the three properties are satisfied by BF4 minus. This is the answer. Yeah. Now let's move on to the next question, that is question number 26. I am giving you ample amount of exercise because this is very important chapter as far as JEE is concerned. So that's why I am giving you as many questions as possible, touching each question, touching each portion of the chapter. Yeah. So next question would be, we have to, 4 statements are given and you have to select the incorrect statement. So first statement given is, in ClO4 minus, all ClO bonds are identical and there is strong p-pi d-pi bonding between chlorine and oxygen. So just look at the ClO4 minus structure. So ClO4 structure would be ClO4 minus. Yeah. So ClO4 minus would be something like this. O minus, so it has no lone pair, sp3, 4 bond pair, no lone pair, sp3 hybridization, tetrahedral in shape. However, it has equal 4 resonating structure because this density can shift here and any of these 3 bond can shift here, so it has 4 resonating structure or 4 equal stability resonating structure, and therefore it is all the ClO bond length would be equal in this case, which would be equal to the bond order would be equals to the 7, that is the number of covalent bond pair that are participating upon the number of resonating structure, that is 4. So the bond order would be 1.75 in this case, and all bond lengths are equal, and there would also be a p pi d pi bonding taking place in this case, because it is coming here because it has vacant d orbital and these electrons are present in the p orbital, so it can only happen if there are vacant d orbitals here. So electrons comes here and the electron density shifts from here, so there is p pi d pi bonding in ClO4 minus also. So the A option given is correct. We have to choose the incorrect statement. The second option given is in P4S3 molecule, the molecule given is P4S3, it is said that there are 6 PS bonds, 3 PP bonds, that is 6 PS bonds, 3 PP bond and 10 lone pair in total. So first we have to determine the structure of P4S3. Most of the cases when the number of central atom is greater than 2, most of the time the structure comes out to be cyclic. So in case of P4S3, it would be P, S, P, S, P, S. So 3S we have considered and 4P, and 1P comes something like this. This is not planar, I can say you, but I have to draw it something like this because I cannot draw a 3D structure in bold. So this is something like this because all this has one lone pair, this is one lone pair, one here, so it is hybridization of sp3 with one lone pair and 3 bond pair that is bent in shape, and this has each sulfur has 2 lone pairs, so 2, 2, 2, 6 plus 4, that is 10 lone pairs in total, 6 PS bonds and 3 PP bonds. So the statement given is correct. So we have to choose the incorrect statement. The third statement given is that in N2H4 is pyramidal over about each n atom. So let's consider the structure of N2H4. N2H4 is also known as a hydrazine. So N2H4 is this, and this. So it would be something like this, NH2, NH2. So this has one lone pair, this has one lone pair. So 3 bond pair, 1 lone pair is strike number 4, hybridization sp3, and since it is therefore it is bend shaped, that is pyramidal with each respect. So this statement is also correct. The next statement is the Br2 and ICl have the same number of electrons and thus both have nearly the same boiling point. However, sorry, this is sp3 hybridization and this is not pyramidal, this is bent about each, so this is totally wrong. So Br2 and ICl have the same boiling point because they are possessing the same number of electrons and also their molecular mass is quite the same. Br2, the molecular mass of Br2 is 160 and the molecular mass of ICl would be 127 plus 35, that is 162. So the molecular mass is almost the same and the number of electrons is also the same. So the boiling point would be same because the boiling point is directly proportional to the van der Waals forces, and van der Waals forces in turn is directly proportional to the molecular weight. So the incorrect statement was that the N2H4 is pyramidal about each other, that is false. Yeah. So this was the question number 26. Now let's move on to the next question, that is question number 27. Question number 27 would be which of the following compounds contain both ionic and covalent compounds. So one option is the CuSO4.5H2O. This is a very peculiar structure of CuSO4.5H2O. Originally, it doesn't have the 5 molecule of hydration, or I should say the 5 hydration in its crystalline structure. Its original molecular formula is CuH2O4 here SO4, and there is only 1 water of crystallization in this. So its correct formula is like this. So if someone asks this, there is only 1 water of crystallization in CuSO4.5H2O. So its structure is something like this. This is Cu, then this is oxygen which is bonded through the coordinate bond, which you will learn more in the coordinate compounds. This is oxygen, this is hydrogen, hydrogen here, there is oxygen here also, hydrogen, hydrogen, there is oxygen here also, and 2 hydrogen So Cu is in +2 oxidation state. So these are the 4 H2O, and the next one H2O water of crystallization is hydrogen bonded with these hydrogens of the hydrogen that are attached by coordinate bond to the copper ion, copper +2 ions. This is how the structure of the CuSO4. This is the structure of CuSO4 2 plus H2O, and SO4 2 minus is the rest. So it has the ionic bonds also and the covalent bonds also. This was the question number 27. So just keep in mind the structure of CuSO4.5 H2O, because this has been asked in JEE 2009 that how many H2O molecules are directly attached to the Cu ions, and the correct answer was 4. So this structure can directly be asked in JEE. This was question number 27. The next question, that is question number 28. Question number 28 is the match the column format. So you are given 4 compounds, 4 molecules, B2, N2, O2 plus and C2, and the properties according are given as paramagnetic, diamagnetic, bond order less than 2, contain 2 pi bonds, and one last property is that stability more than O2. So first thing to note that B2 we know is paramagnetic because it has 2 electrons, each of the 101 electrons in the pi orbital of 2px, anti-bonding electrons of this, so it is paramagnetic. So definitely this is P, Q, R, S and T. So it would have P option here. We know N2 is diamagnetic and have a bond order of 3. So it is diamagnetic. O2 plus is paramagnetic, have 1 unpaired electron in the anti-bonding pi orbital, so it would be paramagnetic, and C2 in turn is diamagnetic. So PQ would be first thing, and then the bond order of B2 we know is 1 because it is sigma 1s2, then sigma star 1s2, sigma 2s2, sigma star 2s2, then pi 2 px1 and pi 2 py. So its number of bonding orbitals exceed antibonding orbitals by 2, so its bond order is 1, so it will have R. But N2 has a bond order of 3, so it will not have the option R. O2 plus has the bond order 2.5, so it will not be here also, and C2 has the bond order 2, so our option will be here also. Contain 2 pi bonds. This was what I was explaining while explaining the structure of C2, that it has 2 pi bonds and no sigma bond, so this will contain S, and O2 plus 2.5, this will also contain S. It will have the 2 pi bonds, N2 have the 2 pi bonds, and B2 will not have 2 pi bonds. Stability more than O2, so the compound having more bond order than O2 will definitely be more stabilized than the N2, so definitely the T would be here. Now the thing to consider that C2 has bond order 2 and the oxygen also has the bond order 2, but the antibonding electrons in C2 would be 4 and bonding electrons in C2 would be 8, and antibonding electrons in oxygen would be, what you can say is sigma 2px, sigma 2py2 and pi 2py2 and pi 2pz2, so it contains about 14, so 6, and so antibonding electrons in O2 is greater than the antibonding electrons in C2 because 2 electrons are extra in that pi star 2px and 2py, therefore C2 would be more stable as compared to O2. So this is the answer. B2 is matched to P and R, that is paramagnetic and have the bond order less than equals to 2. N2 is matched to the diamagnetic, contains 2 pi bonds and stability more than O2 because it has bond order 3 and O2 has a bond order 2, and bond order is directly proportional to the stability of the molecule. O2 plus has the bond order 2.5, so definitely it is more stable than O2, and the S contain 2 pi bonds and the P is a paramagnetic species. C2 is diamagnetic, has the bond order 2, contain 2 pi bonds, both the bonds are the pi bonds, and stability more than O2. So this was the measure column. This can be asked in the JEE also because in the 2009 little bit similar to this has been asked in JEE 2009, commenting on the molecular orbital theory. So the next question is an assertion reason, that is question number 28. The assertion reason, the statement 1 says that the all FSF angles in SF4 are greater than 90 but less than 180 degrees. So first consider what would be the hybridization of SF4. It will have 4 bond pair, 1 lone pair, sp3d hybridization, and the structure would be seesaw. So it would be something like this. S and the lone pair would reside at the equatorial position. This I have explained in the foundation level of chemical bonding, that why it is there, because the lone pair bond pair repulsion would be more and would be less in this case. So this is the SF4. So this would, because of this repulsion, there would be something distortion here also. So the question is that all are greater than 90 degree. However, this is not the case, because this angle would in turn would be less than 90 degree. The second statement says that the bond pair lone pair repulsion is weaker than the lone pair bond pair repulsion is weaker than the bond pair lone pair repulsion, which is in turn true. So the second statement is true, but the first statement that all the bond angles are greater than 90 degree, it is not true, because it is a seesaw structure and this angle is less than 90 degree because of this lone pair bond pair repulsion. So the correct answer would be D, that the statement 1 is false and the statement 2 is true. Yeah. So now I will take some questions on which have been asked in previous years in JEE. So the illustration question number 29, and it has been asked in JEE 2000 screening 2000. The question is the number of POP bonds in tricyclic metaphosphoric acid. So first thing you have to determine what is the tricyclic metaphosphoric acid. So metaphosphoric, 1 unit of metaphosphoric acid would be HPO3. This is we called as a metaphosphoric acid, and tri, therefore it is thrice, that is H3P3O9. So you have to comment on the number of POP bonds present in this. So structure for this would be cyclic, because the greater there are, generally if their central atom is greater than 2, then the structure comes out to be cyclic. So it would be PO, 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 and yeah, here it is O, and here it is P, and here it is O. Yeah. So this would be the 6-membered ring formed. This is H3, and then it would be double bond here, double bond here, double bond here, and OH, OH, OH. So this would be the structure for metaphosphoric acid H3P3O9. And the question is the number of POP bonds. So the number of POP bonds is 1, 2 and 3. So the correct answer is 3, and the option given was the C. So this is the correct answer. The next question that has been asked in JEE is question number 30, and it was asked in JEE 2000 again. JEE 2000, that out of amongst H2O, H2S, H2CE and H2TE, the one with the highest boiling point, H2O, H2S, H2SE and H2TE. So the few points to be remembered is that boiling point is directly proportional to the molecular mass of the molecule. So molecular mass of H2TE is greater than the molecular mass of H2SE, which is greater than the molecular mass H2S, and the least molecular mass is of H2O. So definitely the boiling point of H2TE is greater than H2SE, greater than H2S and greater than H2O. You can say like that, but in H2O there is, you have to consider the intermolecular hydrogen bonding also. Because of this interaction, the boiling point of H2O is greater than H2TE, that is this hydrogen bond, that is the dipole-dipole interaction overcomes the van der Waals attraction for H2TE, and that's why the H2O has the highest boiling point because of hydrogen bonding. This is the A option. So this is the correct answer, that H2O is the highest boiling point. The next question is question number 31. This is also asked in JEE, that is JEE 2001, that is the assertion reason. Question number 31, JEE 2001. The first statement is that between SiCl4 and CCl4 only SiCl4 reacts with H2O. That is true, that because the Si has the vacant d orbital on which the lone pair of H2O can attack, and the reaction occurs, that is the hydrolysis of SiCl4 through the coordinate bond formation. However, in CCl4 there is no such presence of the vacant d orbital, therefore it does not react with H2O, and therefore the statement 1 is true. The statement 2 says that the SiCl4 is ionic and SiCl4 is covalent. That is false, because SiCl4 is also a covalent compound and CCl4 is also a covalent compound. Therefore, the statement 1 is true, but the statement 2 is false. Therefore, the correct option would be C. That the statement 1 is false, and statement 1 is true, and statement 2 is false. So, let's take another question that is been asked in the recent years. Question number 32, that has been asked in JEE 2007 about again accession reason. The first statement is boron always forms covalent bond. The first statement true, because boron always forms a covalent bond. The second statement is the small size of B plus 3 favors formation of covalent bond. The smaller the size of the cation, more would be the polarization of the anion and more would be the covalent character. So that's why the boron forms the covalent. All the compounds of boron are covalent in nature, and the statement 1 is true, statement 2 is true, and statement 2 correctly explains the statement 1. That's why the option selected should be A. Question number 33, and I think this would be the last question for this module. The question is the nitrogen oxide that contains NN bond. Nitrogen oxide that can contain NN bond, the first option given is N2O. So the structure for N2O would be something like this, that NN bond, double bond here and double bond O, and here it would be plus charge, or this most stable would be this, that NN, the negative charge resides on the oxygen ion. There is one more resonating structure to this, that is this comes here and the electron density shifts on this nitrogen, so it will be O double bond N double bond plus, it would be double bond N minus. However, the more stable resonating structure in this case would be this one, because the negative charge is residing on the more electronegative atom, that is oxygen. However, in this case it is residing on the less electronegative atom, nitrogen. Therefore, the contribution of this structure to the stability, contribution of this structure to the final structure would be more than this. So it has the NN bond. So option A is correct. Option B is N2O3. So generally, if you are asked about the N2O3, you will draw something like this, that N double bond O, and this doesn't have the NN bond. However, this structure is not correct. It is an exception. You can say the structure contains an NN bond, and it is double bond O here and double bond O here, and there is a DT bond, that is O here. So it has one lone pair, but it has no lone pair. It is connected to this. If you replace this coordinate bond by a single covalent bond, then this would have plus charge and this would have minus charge. So it has the NN bond, and this has been asked in JEE. So it is an exception structure. This is the correct. So this has the NN bond. So option B is also correct. The option C given is N2O4. So N2O4, the structure of N2O4 is N double bond, this O, there is O and there is O. So there is this double bond, and this is what you can say double bond O and double bond O, and this is here. So this is the structure for N2O4, and if you replace it with the negative and positive covalent bond, then it would form something like this. So it has the single covalent bond, that is NN bond here. So option C is also correct, and option D given was N2O5. So the structure for the N2O5 would be NO N double bond O, and this has double O, and this is so this is the structure for N2O5, and it doesn't have any NN bond, so option D would not be selected. So the A, B, C are the right option which have the NN bond, and D does not have the NN bond. So you can see that directly exceptions are also asked in JEE, so it is quite better to just remember some of these exceptions, so this can help you. So this was the last illustration, and I just have to mention that question number 1. In one question was also asked in JEE 2009 about the number of water molecules that were directly attached to CuSO4.5H2O. In that number of water molecules that are directly attached to the copper ion, and I have said that there is only one water of crystallization. In that case, only 4 H2 molecules were directly attached to the copper ion. So I think I have taken ample amount of illustrations on this chemical bonding, and hope you enjoyed the lecture. Thanks.